Om Shri Sai Ram, offering my loving salutations at the lotus feet of our Divine Chancellor. I welcome all of you to the afternoon session of the first day of this two-day webinar on physics for healthcare. We had a wonderful session in the morning with the inaugural session and the three speakers giving us a lot of insights into how physics is being used in the diagnostics and therapy related to healthcare. I'm sure the afternoon session is also going to be very, very interesting. The first speaker for this afternoon session is Professor Antonio Pifferi from Italy. Professor Antonio Pifferi received his PhD in physics from Politecnico di Milano in 1995 and is currently a professor in the Department of Physics in Politecnico di Milano, Italy. He is also the director of the Center for Ultrafast Science and Biomedical Optics, which belongs to the European Union network of laser infrastructures, the Laser Lab Europe. He is a leading expert in the field of near-infrared spectroscopy and diffuse optics. His research activity is focused on the study of photon propagation through highly diffusive media in the visible and near-infrared range, using time-resolved techniques leading to picosecond temporal resolution with sensitivity down to the single photon level. He has been pivotal in developing the field both vertically, from basic research up to exploitation of new application directions, and horizontally, that is covering diverse approaches and applications ranging from optical mammography to functional brain imaging, from food analysis to monitoring of waste products. Over the years, he has enabled a strong and impactful translation of basic research, for instance, fundamental studies on time domain diffuse optics, to clinical, for instance, functional brain imaging, optical mammography, etc., and leading to industrial commercialization. With more than 10,000 citations and an H index of 59, is among the top most scientists in the field of biophotonics. He is also the director of the Laser Lab. Over the last 5 years, he has been involved in more than 7 projects funded by the European Union, an Italian project, an industrial project with Japan, and is also responsible for the initiation of two startups aimed at providing commercial solutions to single photon detection and compact, robust clinical diagnostic devices based on diffuse optics. He has broad experience in supervising PhD students and postdoctoral researchers, and also is an inspiration to students for his simplicity, humility, and ethical approach to research. In particular, he has been involved in 3 Marie Curie ITN projects, which is one of the Europe's most competitive and prestigious research and innovation fellowships as principal investigator. The fact that the 4 PhD students that he had guided under this Marie Curie projects are from our esteemed institution, Sri Sathya Sai Institute of Higher Learning, is a demonstration of his faith and confidence in the value-based education of SSSIHL. We are indeed honored, sir, that you are with us today and you have consented to give your talk in this two-day webinar. And I'm sure yours will be an inspiration to all the students and researchers all over the world. I now invite Professor Antonio to deliver his talk on the topic Time Domain Diffuse Optics for Non-invasive Clinical Diagnostics. Over to you, sir. Thank you.
Okay. First, we'd like to double check whether you can see my presentation and you can hear me.
Yes, sir. We are able to hear you. We are seeing you rightly. Currently, we are seeing you. Presentation is also coming. Yes, presentation is also coming.
Okay.
Yes,
well,
sir.
I'm very happy and I would say I'm honored to be here because this is a great opportunity for me. I have a long tradition of interaction with mostly your students and it has been after so many years of collaboration, an honor to be able to present some latest results on our group in this great webinar. I could not attend the webinar from the beginning, but I followed that on YouTube, and I was impressed, absolutely impressed by the beauty of the initial celebration and by the strength of the three initial speeches, which I completely agree. So this also gives me a lot of enthusiasm to go on with this research activity for the good of humankind, of mankind, of humanity, and it's really inspiring to me a lot on going on this activity. Well, now I move to my presentation. This is focalized on time domain diffuse optics for non-invasive clinical diagnostics. That is a particular field, maybe not so known. It is a niche application in a way, but that can have a great impact in the future. And I would like to just state that we just close one. Okay, I would like just to state that we are part, as has been said in the two, let's say, enthusiastic introduction to my talk, that we are part of Laser Lab Europe, that is a network of the laser infrastructure through Europe. And this is a facility within the Polytechnic of Milano and can offer access to our labs. And recently, it was extended access also to non-EU countries, so it's possible to apply for 1 or 2 weeks joint experiments with the EU, covering a full travel and also access to the facility. And okay, we are part internally of a group on photonics for health, food, and cultural heritage. That is a group of large group at Politecnico dealing with the specific applications of photonics in different fields. The index of my presentation is I just start the timer. Basically, we'll give a introduction on diffuse optics. Then a few concepts on the physics beneath that. Then we'll focalize on 3 applications: breast, brain, and tissue spectroscopy. Then some hints on technology, where technology is going, standardization, that I think is an important issue in this respect, and finally, perspective and conclusions. Well, diffuse optics, we are basically dealing with the propagation of light into diffusive media, in particular biological tissues. So if you think to a standard clear medium, light will go straight through that without being diffused. Conversely, if you just put a small drop of milk into a cuvette, you will see that the light is diffused, and this is because of scattering. So scattering basically is related to the fact that photons are deflected from the straight path, and it makes a random path of photons in the medium. You can come up to these 2 parameters, absorption coefficient and scattering coefficient. The 2 of them have different links to the internal structure of the body. In particular, absorption is more related to composition and to chemical species that absorb in the medium, while scattering to microstructure, meaning that the fine structure of the cells, the mitochondria, the organelles will basically create discontinuities in the refractive index, and therefore the phenomenon of diffusion. It is nice to consider that you cannot see through the human body just because of scattering. If you look at the absorption in the wavelength range between 600 up to 1 micron, the absorption of the key constituents that are blood, water, lipids, and others, proteins, are not so high. In the sense that if there were no scattering at all in your tissue, you could see through the body as if it were a colored glass, like a bottle of, like a bottle where you can just see through that with some color. You could clearly see your heart, and even your brain you could see. And what is more interesting is that you could even see the activity of the brain, because when you think to something and you require some intensity of the mental activity, you require blood, and you require in particular oxygenated blood. And when hemoglobin links to oxygen, it changes the color, basically. It changes the properties, as you see here on the blue and the red lines. That is how the blood is changed when you get oxygen. That means that if there were no scattering in your body, then you could clearly see your brain, and your brain, what is going on inside. If you make a movement like this with your hand, you would see on the other side, on the opposite side, some flashing that is due to the requirement of oxygenated blood from the brain. And this is our realm. That is, this is the physics, this is the environment where we work, where I've been working so far. I mean, basically, I've done nothing in my life apart from this in terms of scientific achievement. So it's really focused on this particular aspect. And if we recall briefly the physics behind, it's all based on the radiative transport equation. That is a balance equation that you can encounter in many other cases. Also, for instance, on the study of diffusion of electrons, and in many different instances. And basically, it's the conservation of energy in a small volume within your body. And it is based on the particle description of photons. And so you consider a small volume, a direction, and you make a balance of photons entering and exiting that small volume. So the first terms, of course, is the gradient of the number of photons, n, of the photon density. That is basically the difference between the input and output photons. So this tells you what's changed in terms of photons that are going in and going out. Then you can have, of course, absorption in the tissue because of chromophores, as we have seen earlier. And a negative term, another negative term instead is scattering, that implies a photon to be not absorbed but deflected to the other direction. So we cannot consider that in the whole balance. And then you have the opposite terms. Photons that are scattered from other parts of your body and enter that particular volume. And eventually, there is the green term, that is the light source. So photons that are generated inside, this can happen because of illumination, for instance, for an optical fiber. All the techniques that I will discuss in the following are non-invasive, in the sense that typically light is injected and collected through optical fibers that you just put on the surface of your skin. And so this source is basically light that is injected through an optical fiber, typically of a laser. Okay, I will just have two more introductory slides on physics, and then I move to applications, because I would like to highlight two key concepts that are the basic concept on which I've constructed we have constructed all the different applications so far. First concept is that absorption and scattering alter the photon time distribution. So I have to say that there are different approaches to study photon propagation through biological tissues and diffusive media, and we were just choosing one, that is time domain. Time domain, it's not the only one. You could also follow other approaches like frequency domain or just CW with a continuous wave, but our peculiarity is, and our excellence in a way, is to pursue this approach that is more complicated but rich of information. So the basic idea is that you inject a short laser pulse into the medium, and photons will travel different paths. And so in the end, you see up here in this red curve, you can see that the photon temporal distribution is broadened because photons will follow different paths. What is important is that this photon temporal distribution, that is what eventually we measure, so the collection of photon arrival times, is strongly dependent on absorption and scattering properties, but in a different way. In the sense that absorption affects mainly the tail, while scattering mainly the peak. And again, if we consider that absorption and scattering are linked to different aspects of your tissue, composition and microstructure, we can separate these two effects. So the very first point is that we can distinguish absorption from scattering on the basis of photon temporal distribution. An implication is that we are not sensitive at all to the optical properties of the surface. On the right, you see an apple with and without the skin, and basically the absorption is just the same. This is very important in real life, meaning that we are not at all dependent on skin pigmentation. We're not depending on laser instabilities, on optical contacts. So the measurement is robust also in a real environment. Second concept, time and cold space. That means that if we increase the photon propagation time, the depth visited by photons is larger and larger. This is important because many measurements will be done in reflectance, meaning that we just look at the body from the outside and we make a kind of ultrasound echography. So we would like to get an echo of photons that go back after being injected. And we can see that the longer the time the photon spent in the medium, the deeper the depth that it could reach. And I will move now to the applications. So behind everything, there is always the measurements in the time domain. So this is our peculiarity, our expertise. But then we will retrieve the optical properties, absorption, scattering, and follow them in as a function of wavelength. This is spectroscopy. As a function of space, this is imaging. As a function of time, not the photon propagation time, but the laboratory time, and this is monitoring. I will show one example for each of them. First, imaging breast, because the key application is optical mammography. Optical mammography means that we scan the compressed breast using this approach. So we do measurements in the transmittance with the goal to detect breast cancer. It's very important because breast cancer is the cancer that can be cured if is detected early, and detection is fundamental. So that's why a lot of interest was moved in this region. I just would like to point out here the wavelengths that were used, 7 wavelengths, because we have different constituents. We have, for instance, water that is around 980 as a peak, then lipids, 930, the yellow one, and then the 2 forms of bloods, and then also collagen. And so by combining different wavelengths in this range, we can identify different constituents. These are examples of images. On the left, you see the late gate intensity, and you can clearly see that at different wavelengths, there are different kind of contrast. In this case, we have, fortunately, a tumor, and that can be seen from the X-ray mammography. And on the right, given what I showed earlier, the link between absorption and constituents through the extinction spectra, we can reconstruct the composition of these lesions in terms of blood, different forms of blood, oxygenated and unoxygenated, lipid, water, and collagen, we were among the first to measure collagen because of this is a tiny absorber, and it's very important, as you will see, and that was thanks to the spectral coverage. In most cases, optical mammography is performed only at the 2 wavelengths where we can see the blood, and we were the first to pioneer the measurements in the region above 900 so that we can get also these components. You can clearly identify that we do not have a good spatial resolution. This is absolutely a limitation of the technique, and there is basic fundamental physics there, and we have a resolution around 1 centimeter, so at all not okay for, not comparable with X-rays. On the contrary, our key added value is tissue composition, that it's not easy to get through imaging, other imaging modalities. So this is done non-invasively. And okay, we can also differentiate the benign lesion. This is a cyst, so something that absolutely has no harm. And we can basically detect that on the basis of the scattering that creates this shadow, darker shadow. And okay, a clinical study, I mean, actually we have done 3 clinical studies so far. This is one with 200 patients, and we can differentiate malignant from benign lesions and detect them. Okay, to make a point here, I would say that because of resolution, our technique is not enough to detect cancer, because you need to detect that in an early stage when it is lower than 1 centimeter, and for that we do not have enough spatial resolution, that we have to admit. What we can add, as I said, is characterization, so it can be a second choice technique to go together with others like ultrasounds or X-rays for the characterization of the lesion to add some value. Another application, even on breast, is something that I like a lot because it is before diagnosis. It's before, it's something for prevention. It is before the cancer is grown. And you see here, these are measurements of spectroscopy with our system, 5 different types of breasts. And you can clearly see that this 5 person had quite different absorption on the left and scattering on the right breast spectra. And I don't go in detail. We have the different composition, water, lipids, blood. So basically the key difference is blood, but also collagen. We have not set that here, but it's also there. And the key point is that you can clearly differentiate that. But behind that, there is something important, because it is well known from literature that if you have a fibrous breast, that is a breast that in particular is opaque to X-rays, it has a high density, X-ray density, there is a higher risk of getting cancer. 5 to 6, depending on the amount of fibrous. So it's normal breast, just normal breast. In most cases, nothing happens, but you get a high risk in your life. The good point is that since if you detect the cancer in early stage, you have a early stage with no involvement of lymph nodes, you have a survival rate up to 95%, so much. And also you have the possibility to have a small intervention with a very, very small compromise of the breast. And so basically you go home and hopefully the disease is over. And of course, it's completely different if that is an advanced stage. But the key point is that if you can identify a part of population that is more at risk, then you can concentrate more prevention that. So you cannot use very sophisticated techniques on all the population. So what a key oncologist told us is, if I know that a part of the population is more at risk, then I can follow them more closely, and when the cancer comes out, I intervene and take that over. So being able to stratify the population, so to identify risk is important. And just to show that, again, a study of over 250 patients, and we can see that we can basically detect a good correlation between the optical measurements and breast density. That means that we can give this, let's say, kind of information to the clinicians. And we have to consider that optics is non-invasive first, and then I showed you a very large instrument, but it can be made very compact, portable, and low cost. And there is still another fascinating point here. As I already told you, there is a correlation between breast cancer and breast density. And also, we have shown that we can see a correlation between our optical measurement, in particular collagen, and breast density. There is certain number of papers in science that is in literature that points to the fact that collagen could be linked to the onset of breast cancer. It's linked to the fibrosity and to the fact that it can be transformation of the tissue that leads to breast cancer. So our question is collagen a direct risk factor for breast cancer? So not something indirectly linked to the fact that more X-ray dense breast leads also to some more collagen, but collagen itself is a key factor. These are just preliminary data, and we don't have the statistical power to draw any conclusion here at all, just an observation. We were just classifying women, both with breast and without breast. Those who unfortunately had breast are in red, the normal one are in blue, and we are classifying that on the basis of the X-ray density and on the basis of the collagen. What is strange, not strange, what is expected is that if you have high density, so all the person on the right, in particular you select the 10% of women with more density, you see that out of that 10%, only 2 of them are normal. That means that there is a higher occurrence of cancer if you have a high density of your X-ray. That is what the literature tells us. But the same happens with the collagen. If you see that now it's the top region, for high collagen, there are more cancer than normal. What is interesting is that these two families, these two groups are not overlapped completely. That means that collagen could be independent risk factor. This is very important for 2 reasons. First, because it's possible to go on research and find out the link between collagen and cancer. And second point, because you can use data to reinforce the stratification. So the more precise you are on the risk factor, the more you can devote to that woman and the more you can try to help her in case cancer comes out. I move now to a different subject, the brain. And so again, this is a prototype that was constructed in our lab. Basically, the measurement is simple. You have an helmet here, and you have fibers that inject light and other fibers, or better, fiber bundles that collect light. Everything then is measured. And okay, I have not spent time on explaining how we do the measurements. There was a slide before, but I was not commenting that detail. So basically, the idea is to have pulsed lasers. In particular, here we are using semiconductor model-locked lasers and coupled to fibers. Power is not so much, it's a few milliwatts, so absolutely non-invasive. And then we collect photons remitted at some distance through bundles. And then there is a system for time-correlated single photon counting, in the sense that we collect every single photon one by one and attach a timestamp on the photon arrival time, and then we create an histogram out of that. And well, here you can see that by doing these measurements in time meaning following the optical properties as change in time, you can recover the trend of oxy and deoxyhemoglobin that are linked to the presence of oxygen or not. And you can clearly see that during the task, and here the task is just a movement of your hand, grasping on the ball. And when you do the task, the brain requires oxygen on the other side of the hand. And therefore, you see an increase of oxyhemoglobin, while the red one, while you have a decrease of the oxyhemoglobin, that is the blue one. There is a latency of a few seconds, 2-3 seconds, and also when you interrupt the exercise, there is then a slow recovering down to baseline. Here, the concept is the second concept we are exploiting, the fact that timing costs depth, and so for longer late photons, so those that traveled more, we can go deep into the brain and see what's happening there. Just to confirm, this is validation against MRI, a co-registration of optical signal against the magnetic resonance, functional magnetic resonance imaging signals. So basically this concept is exactly the same as what you see in fMRI. In fMRI, you see the bold signal that is related only to the oxyhemoglobin. And, but basically you see that the two measurements, the MRI one on the top and the optical one on the bottom, are overlapped. There are two differences. First, again, we do not have the same spatial resolution of MRI. So yes, we can create maps, but not, it's more topologies we can create, not really high resolution images. And, but on the contrary, we have two advantages. First, that optics can be made very compact. And for instance, you can think of using that also in real life. It is used a lot, this, for instance, for psychology. And you could think of using a kind of helmet to understand the learning process in the mind and help in case there are impairments. And yeah, the other difference is that we can see also oxyhemoglobin that is not observed by MRI. But the kind of information is very similar, and so here we were basically validating that. We can use that also in patients, and don't go in detail, but basically these were epileptic patients, and basically the measurement done using optics is overlapped by the response that can be seen using fMRI. Just to show here an application, another application, here we are developing new photomultipliers, or better, these are called the silicon multipliers, SIPM. We were just, let's say, getting the advantage of technology because these detectors were developed for PET or for higher energy physics. And so we were just grabbing what technology offered us, and our only merit was to adapt that to diffuse optics. It looks like they can work well, and we could develop compact ones that can be directly put in place with the brain. And this led us to create this tomograph, meaning that using a single source and 8 detectors in place, we can create a kind of tomography. The one that you see on the right is a slice at the level of the brain cortex. And when you see the dark zone is an activation of the brain. I'm doing basically a finger tapping exercise. So I'm just moving the fingers of my right hand. And on the left, I can see when there is the task, this activation. Okay, third application is spectroscopy, tissue spectroscopy. And I'm very proud to say that this system was developed by Dr. Sanatana Kunugolo, who comes from SSSIHL. So, I mean, I will say a few words on that later on also. So this is basically all his work. I will just present a part of what was achieved, because I prefer not to present another field on Raman that is very important, but I had no time for that. But basically, all this part is his job. And okay, again here we have a laser. Now this is a supercontinuum laser, and we can slice that using spectral selection. So the key advantage here is that we can cover a broad range with an automatic tuning. Basically, this is a unique system. So far, I'm not sure there are other systems with the same performances, and also we could make it in rec, so that it can, now it's moved in clinics, and Pranav, who is another alumnus of Pranav Lanka of SSI HL, is looking after that, and we will see something later on. And just to see what we can do with that, we can, the idea is to have a non-invasive detection of absorption and scattering. And here, for instance, we were studying the abdomen, and we can clearly see that there are differences depending on the thickness of the first layer on the abdomen, or as a function of age, and these are related to water, lipids, blood itself, and so on. I don't go into detail in these results. The only point that I would like to point out is this. Why are we looking at fat? Because there is an increasing interest in the fat, so that people are starting saying that it is an organ, in the sense that if it works well or bad, it depends a lot on the diseases that we can encounter in our life. Okay, it's well known that there is a strong link between health and food and lifestyle. What I think we are starting understanding and deciphering now is the exact link at the biochemical level, at the epidemiological level. There are a lot of studies now trying to relate all these factors in a scientific way, in a rigorous way, and in particular combining different disciplines to the onset of different illnesses. And not just diabetes, but also cancer, cardiovascular diseases, sarcopenia, but also neurological diseases. I heard that also Parkinson and Alzheimer are somehow related to what happens at the level of metabolism, and in particular at the level of the fat tissue, meaning that an alteration of the standard metabolism can lead to what they call the inflammaging. That is a complex of mechanism that involve also the autoimmune response of our body, a general inflammation that eventually create toxins and can lead to different diseases in your body. So there is a lot of interest on this research in Europe, because, but this is everywhere, I think, in the world, of the increasing cost of healthcare and the fact that we need to help everyone. And so the obvious choice is not to get ill. And there are many diseases that can be cured, but many of them can be prevented. I heard that maybe 50% of diseases can be prevented through a proper food and lifestyles. And what is not clear is really the link and how to use that so that we can prevent instead of cure diseases. That is why we think that diffuse optics could help in giving a feedback to the clinician, to first for basic research to understand what is going on, and then for helping the patient itself. Okay, very quickly, the lung. The lung is something new. Also with Dr. Pranav Lanka, we are facing that, and we are trying to explore this as a feasibility, because it has not been studied so far using diffuse optics, because it's deep and it's not well known. So the key idea is that there are many diseases that can be linked to lung, COVID, of course, has this also effect, and they are more or less related to the density. And so if we were able to see the internal structure of the lung and the composition and the density, we could try to help in monitoring these diseases. These are just preliminary measurements. We can see from here that we first started from a broadband characterization of the thorax. This is important because the possibility to reach a lung depends on the optical properties of the upper layer. And we were running then simulation that shows that in principle, yes, it's possible to reach that out of these optical properties. And so we're trying a validation protocol to see whether we are sensitive. So just an inspiration protocol, very simple, with the idea that if we take air in principle, absorption should be reduced because of the dilution on the tissue. And this is an in vivo exercise on 5 subjects. And I don't go in detail, but basically, in the in phase, there is inspiration. The out phase, there is exploration. And we see something that is task related. So there is some hint that it's possible. We have to state clearly that it's not so clear, meaning in the sense that there is not 100% consistency. In some positions, there is not really the same aspect that we would expect, and differences among different subjects. We are studying that, so there is the idea that possibly we can reach the lung, but there are many confounding effects. So it's just a new field that is just started, and we will see in future what could be possible to do. Briefly, I go to technology. I would like just to mention here that the technology is advancing at a great pace. And here it's not our merit, but the fact that we are exploiting the great advantage in photonics, in particular in the telecommunication, that are reducing the size of components down and permit integration. So this is the very first system when I was working 30 years ago, basically, when I started my activity. And it was a large laboratory with high power lasers. Yeah. Second generation clinical prototypes, those that I've shown you so far, and these are smaller, still large but portable, and the key advantage was linked to the semiconductor laser that permitted us to enter the clinics, so to go to clinics. Third generation, battery operated wireless boxes, and this is the size. We also were funding a spin-off company of Polytechnic Milano, Pioneers, for developing these devices that can be operated in real life. And this is the fourth generation. The idea is to squeeze everything into something like a finger. So the smart opto is something that can do all what I've shown you earlier in terms of application. And we have 8 of these. This is a European project for optical mammography to combine ultrasound and optics. And a final point is to go towards the conclusion: performance assessment and standardization. This is something I really a lot motivated, because I think that we can win and we can get important results for humanity if we join efforts and we coordinate, and if we try really to go to let's say rigorous assessment of our technology. And this requires necessarily performance assessment for instruments, interlaboratory comparison, and so on. I don't go in big details. This is a story that we constructed at European level during the last 20 years, basically, with a sequence of steps. First, try to formalize the clinical problem into a physical problem. Second, define protocols that needs to be agreed at international level. And then construct phantoms. And I'm extremely proud that He will be also presenting later on in a discussion that Sanatana Kunugolu, who is an alumnus of SSI HL, and now at also Polytechnic. Now he moved to Tyndall. He developed the first company startup developing phantoms, and this is very, very important for the future of biophotonics. Laboratory comparison of instruments. A few words later. It's important to work together and to compare. Clinical comparison skip, and industrial standards. We were involved in 3 industrial standards. That is the final end of that. That should assure quality in the instruments. And this is a particular exercise on multi-laboratory comparison of instruments. This was coordinated by Dr. Pranava Lanka from SSSIHL, who is actually working in my lab. And the idea is first to compare many instruments on the very same phantom kits, action 1. Action 2, open data. So put together all this data obtained by all these instruments and try to share in the scientific community. Third, analysis. So compare different analysis tools so to reach the same agreement. And the protocols and phantoms adopted are this. So 3 protocols again agreed at the European levels, at world level, I would say here, with different features of figure of merits, phantoms, and so far this study enrolled 29 now, one more instruments. What is important is that they are of many different types, and not just time domain. There is also CW, continuous wave, frequency domain, of different application, monitoring, spectroscopy, imaging, different countries. And so it was a big exercise, and we are just about to collect the final results and to publish the data. And in conclusion, I think that diffuse optics has some interesting features. Of course, we have seen many weaknesses, many limitations. We don't want to say that it's a solution for everything, but it has unique features. It is non-invasive, so absolutely you can use everywhere. Chemical specificity, so giving composition that is not so normal. Normally in clinics you have many instruments that are morphology instruments, not much non-invasive, let's say, giving chemical specificity. Functional, how your body is functioning, also metabolics. Non-contact, not shown, but it's also possible to make that non-contact, so remote surveillance. Deep, few centimeter deeps. Operate independent. In the latest achievements, you can have these very small devices that will just give a number. And so you do not need to have, let's say, technicians to operate that. You can use that also for healthcare at home. And this is very important. So you need not the person to reach the hospital, but you could, in a way, get the measurement and have, with the telemedicine, the measurement transferred to an hospital with the doctor that will give some hint. Scalable. You can construct from large laboratories to, now we are in the 1 cubic centimeter dimension, and it could be possible even to squeeze that more to mobile phone possibly applications. And very conclusion on my vision. Okay, I was impressed by the first talk by Professor Gauri Shankar, sorry if I pronounce it badly, on the link between physics and health, and I completely agree on that. And there is kind of complexity in both. And what I admire of other physics, like high energy physics or other physics, is the fact that there is a large international community very joint. Before a new particle is announced, the results are compared among different laboratories all over the world, and this is what makes humanity strong and science strong. So this is my dream, try to improve more and more collaboration at world level so that we will try to solve the big societal problems together and jointly. Of course, there is also in science competitions, but what I learned so far in these years is that there can be normal standard competition together with strong collaboration. And we need to go in that direction for standardization, for performance assessments, for looking together at new problems. With this, I have concluded. I have to acknowledge many people at Politecnico and with collaboration with other institutions. But most of all, now I would like to acknowledge and thank so much SSSIHL, because I had the opportunity and I still have the opportunity to collaborate with the 3 excellent alumni from your great institution that brought a lot in science, and not only in science, because all of us, and not the only one, all the people in the lab appreciated the humanity, the enthusiasm, and the temper of all these great researchers. And yes, with that, I thank you again, and I'm welcome for a good continuation of the webinar. Thanks so much.
Thank you, Professor. It was really a wonderful talk on this diffuse optics. There are a few questions that have come. I will just read out the questions for you. The first question is, what are phantoms? Are they tissue phantoms? That's the first question. And are you making them in your lab?
Okay. Well, this is important, because at the basis there is the idea that this again is related to performance assessment and standardization. Too many times I see instruments that are directly put in the clinics without a rigorous validation, because basically physics is physics, and so you cannot beat the physics law. So you need, before going to the clinics, to have a validation in the lab. And this is less costly. It costs a lot to go into clinics, so you have to build systems, so and so, while in the lab it's more easy. And you can do that using tissue phantoms. Tissue phantoms means that you are simulating basically the optical properties of tissues, like, for instance, absorption through pigments, ink, or scattering through particles. Can even create heterogeneous structures like the one that I show in the right here in this slide. And yeah, this is very important because you can test your instruments there. What is also important is the reproducibility of these phantoms. That's why we are working a lot at international level for that. Fortunately, there was this Biopics company just created by Dr. Sanatana Konugolo, that based in Ireland, and I think we need these initiatives because we need someone who provides us with reliable phantoms. On the other side, we need to calibrate that, more or less like the initial meter that was fundamental for the metrologist and so on, or when we demonstrated that the speed of light is a constant. So we need these standards. We need this reproducible material so that every lab in the world can measure the same and we can go on. Thanks.
The next question is, how are you taking care of hairy skins?
Oof, that is a big
while imaging. How are you taking care of hairy skins while imaging?
That is a big hurdle. Okay, so we are not sensitive to skin pigmentation, so this is not a problem. The problem comes when you get too much hair, so that you cannot have light through. So if I'm doing a measurement on my head, well, I don't have so many hair, so it's not so much a problem. So in my case, it's not a big issue, because if I put some fibers, still some light can pass through. Okay, the key limitation of our system is a resolution. We have a resolution of 1 centimeter, 5 millimeters. So it's not imaging in the sense of millimeter or micron size. So it's not the problem of air that will destroy the resolution of the image. It's more the attenuation. So as far as there is enough light, it's not a problem.
Okay. The next question is, how do you normalize or offset differences in color of the tissue or skin tone, which varies greatly based on ethnic background?
Very good question. Also, because this is something I had yesterday, a meeting on the standardization committee for pulse oximeters, and probably you are aware there were big problems because of papers published on New England Journal of Medicine stating that the reading of the pulse oximeter can be different depending on the skin pigmentation. This, of course, is very, very bad, and it's still not clear from the point of view of results, because they are contradictory studies, but this problem, of course, is very important. I'm happy to say that in our case, we are not dependent on skin properties, just because the effect of absorption and scattering have a different effect on the temporal distribution. So suppose that I change the skin pigmentation, this will just change the total attenuation. It will not have any effect on the temporal shape. As you can see here from this measurement on the Granny Smith apple, it's an apple that is green, and if you remove the skin that is very, very absorbing, a lot absorbing, basically nothing changes, just because it's an analysis that is done in shape and not in amplitude.
One more question, Professor. Can diffuse optics be used to determine quality of food materials? Example, freshness of the fruits or milk, etc.
Yes, it's an interesting question. Also, this one very interesting, and yes, definitely. We can also in our lab we are working a lot on that, and it is in a way fascinating, because you have an easy way, non-invasive, so and so, and of course you get information. What is not yet, what is clear now is that you can see some aspects and not other aspects. What we can see absolutely clear is the color of the pulp. That is in turn related to the ripeness, to problems. Also, if a fruit is going to be rotten, then we can see very well. We can see carotenoids that are important nutrients, so independent of the skin. So even if the skin is a different color, we can clearly identify what is inside. What we cannot measure other parameters like sugar. That was an holy grail in some cases in fruit, because well, people love more sweet. That it's not necessarily more healthy, but this is what the people like. And but for that we don't have good results, and also we do not have good results for firmness. In particular, people in the northern part of Europe loves strong, crispy fruits, and we cannot get that. And so I would say as for now, it is a 50-50. Some parameters we can measure well, yes, basically everything that is related to the color, some others instead not. But it could be interesting because now the devices are getting low cost also in this field, and so I think there could be an important direction there.
One last question from the YouTube channel by, again, one of our alumnus who was in Italy, Vaibhav Bharadwaj. So he says, thanks for the wonderful presentation, Professor Antonio. One question which I have is, how far are we with the miniaturization of the Tdos devices?
Yeah, very interesting. And well, unfortunately, I don't have. Okay, I could have brought other slides, but okay. So we are advancing at a great pace here, and what you see here, it's really something real in the sense that this is a European project that started 2 years ago, and we already have the smart opto. They don't have the photos, sorry, I forgot to bring some, but this is really an object that is existing. It is a couple of cube centimeter, and it is fully autonomous in the sense that we have inside the laser, not a laser, but 8 lasers and a large detector with the full capability. So all of what we have seen previously can be done by this, let's say, single finger, and it can make even smaller, so it can be squeezed even more. So I think we are at a good point there, yes. And yeah.
Any other questions from anyone from the audience? So if there are no other questions, then we once again thank Professor Antonio for this wonderful talk, with a lot of illustrations in terms of the applications that can be there for this diffuse optics. Thank you, sir. Thank you once again from SSIHL for joining us.
Thank you to you for this kind invitation. Thank you so much. Thank you.
Thank you, sir.